Good afternoon. So, we're going to carry on with our chapter 8. I'm hoping that we can finish today. There is one example towards the end. If we don't have time for that, then we'll do that next week. So, last week we looked at different devices and how entropy applies to these devices. We did a few more examples. We stopped last week, sorry, not last week, Monday. Last lecture, we stopped after doing the example on page 8.16. And then there was one example which I said is actually optional, which was the second example. And now we're going to carry on from page 8.17. So, when in the very first lecture, or maybe the second one, in fact, I started talking about diagrams, and I said there are lots of diagrams which are quite useful in showing the behavior of a system. The PV diagram was the most common one that we've used so far. It makes sense, and it's actually quite easy to understand because you understand pressure, you understand the specific volume, so it sort of makes sense how the curve looks like. The other curve which is very important for us is the TS diagram, and obviously we couldn't look at TS until we had introduced the entropy, but when it comes to your second year, third year, you'll actually see that the TS diagram might be even more common than the PV diagram. We're going to see some examples today. So there is actually if you remember the PV diagram, and if you had point 1 and point 2, and then we connected these 2 points by a curve like this, do you remember the area under this curve, what it represented? Do you remember that? Work? Yeah? Okay, so it's displacement work, and we said that because W is P dV, therefore the area under this curve, or the integral if you like, of this curve would give you the work. We have exactly the same concept in TS diagram, so there's an analogy between the PV and the TS diagram, and this is based on this equation. This is the equation which we defined earlier. And then if you rearrange this equation, then you have TdS would give you the amount of Q, which suggests that if you, for example, in this example, if you take the area under the curve in this example, this should give you QR. Remember, R is the reversible, and it just assumes that there are not going to be any losses in the cycle. And of course, you now know why this equation was so common, and we used that a few times in some of the examples that we did. But this is a reversible process. Again, assuming that you're not going to have any losses. What if you have a reversible adiabatic process? We now know that if your process is reversible and adiabatic, it means that it's isentropic. And I said that the reverse is not true. If the process is isentropic, that doesn't necessarily mean that it's adiabatic and reversible. And that is actually emphasized here in this sentence as well. But anyway, as far as the diagram is concerned, if you start thinking about this equation for the entropy, if we assume that there is a reversible heat flux in the problem, then it suggests that if you have a reversible and adiabatic, of course the adiabatic means that there's not going to be any heat transfer. You know that Q is going to be equal to 0, and if that's the case, then of course that equation would be equal to 0. So ds will be equal to 0. So if you combine the reversibility with adiabatic conditions, it's natural that you will end up with zero change of entropy, and your line on the TS diagram would be a completely vertical line. We'll see this actually in an example where we look at a heat engine, and you see exactly how an isentropic process is represented on the TS diagram. The question now is, so what if you have an irreversible process? How do you draw that on the TS diagram? This diagram, and I've emphasized here that it's actually for just illustration, it doesn't have a scientific nature really as such, but just to represent what it means, if you have an irreversible process, of course your Q isn't going to be equal to Q reversible. That's natural. As a result of that, the ds is not going to be equal, and in fact it's going to be bigger than delta Q over T. And as we know, in an irreversible process you always generate entropy, and therefore change of entropy will be bigger than delta Q over T. And of course you can't use this equation anymore. And what that means is that if you think about the area on the curve, the area under the curve that we've got in here, that isn't going to be equal to Q. So you no longer can say is equal to Q, because it's not. And what it means is that if you want to think about it from a, as far as the TS diagram is concerned, think about the fact that if your curve, in this case, or your process has some sort of leaking feature, which means it's actually, some of the Q inside or underneath this curve is actually coming out of this area or leaking through these gaps, and therefore in reality, this area isn't going to be equal to the amount of heat in the process. So while in the previous example, because we had a sort of a solid line, there was no leakage through this area. But here, because in an irreversible process you have some losses, these losses are represented through heat loss, and that's why you can't have that. That equation doesn't apply anymore. So what we conclude by some of these things that we've been saying so far is that entropy change, delta S, between the two states can always be evaluated because entropy is a property. The fact that you can do TS diagram, you can draw a TS diagram, you can define points like that and then try to evaluate entropy is only because entropy is a property. And if it wasn't, you couldn't have done this. Entropy change and absolute temperature cannot always be related. So the relationship between entropy change and absolute temperature is really just TdS equals delta QR, what we've been looking at. Obviously here, you're relating heat and temperature to entropy. What we're saying here is that it's not always the case, and we just showed one example here where you have irreversible processes. So this is not true all the time. It's only possible to relate them if you have a reversible process. And I think we've established that by now, that this equation is only applicable when you have a reversible cycle. Now, let's now start looking at perfect gases and how the TS diagram, how you can draw a TS diagram for perfect gases. In a typical perfect gas, you have these four type of characteristics or states, if you like. Isothermal, temperature is constant. Reversible adiabatic, that is what we know as isentropic. Isobaric, which means the pressure is going to be constant. And of course isochoric, which then means that you're going to have the same volume. So starting with the simple ones, isothermal, of course it means that temperature is not going to change. So as far as the TS diagram is concerned, it's just going to be a horizontal line and therefore no change in temperature. in terms of reversible adiabatic, or what we know as isentropic, again, it's going to be a vertical line, as I mentioned, because entropy is going to be constant. Isobaric and isochoric processes are slightly more complicated because we need to start looking at the equations that we've got for ds when it comes to perfect gases. So in the last lecture and before that, I started deriving some equations for Ts. Remember, we derived this equation and we also derived this equation. And these are the equations that we use for constant pressure and constant volume processes. And you can tell by having Cv and Cp in here. So if you have an isobaric process, of course, the change in pressure is going to be 0. So that term disappears. And because Cp is a constant in a perfect gas, you can actually solve this integration, and that would be equal to S2 minus S1 equal to Cp ln T2 T1. And if you are just interested in T2, you can actually just rearrange this equation in terms of T2 and then get an exponential equation. This explains why you have this type of curve, because it is a typical exponential curve. So T2 and T1 are related through this exponential curve, which is defined in here. If you look at isochoric process, because the volume is not going to change, that disappears. And again, because Cv is a constant in a perfect gas, you can solve this integral. And then if you rearrange the equation for T2, you get a very similar exponential curve for the isochoric process. What you notice, though, there's a difference between the two. They have a different type of gradient, if you like. So this one is steeper compared to this one. In fact, if you start drawing a number of isobaric and isochoric lines on a TS diagram, you see that sort of comparison. So this is how they're compared. The question is, why would you get a sort of a steeper curve for isochoric compared to isobaric? It's explained here, but essentially what we know is that Cp is always bigger than Cv in terms of the actual magnitude when it comes to perfect gases. Then that suggests that if you look at this part and this part of these two equations, then that means that S2 minus S1 over Cp is going to be less than S2 over S1 over Cv, because the denominator is bigger in this one. And if that's the case, then temperature T2 for Cp would be less than temperature 2 for Cv. And you can see from this diagram, I'm going to come back to this, you can see that T2 here is less than T2 here in terms of the actual value. Therefore, this would be on a steeper curve. It's a very loud laugh. Okay, any questions so far? Clear? Good. We now start looking at your favorite topic, heat engines. What's that, oh God? Okay. So, heat engines. 3 examples. In fact, I'm just going to go through this very quickly to put you out of misery. The first 2 cases are just showing why these 2 examples are impossible, based on the second law of thermodynamics. We've done that before. We established why some of the heat engines are not possible and are impossible, but not from an entropy point of view. So this is just looking at that. It's actually quite simple. So look at this heat engine. There is no cold reservoir here. And if we say that the change in entropy is related to Q divided by T, here delta S1 is equal to minus Q1 over T1. Can you tell me why there's a negative sign in here? Why do we have this negative sign? Do you remember the convention for heat? If your system loses heat, that is negative heat, right? So in this case, that Q is coming out of the hot reservoir. So if the hot reservoir is your system, then because it's losing heat, therefore it's going to be minus Q. And delta S will be minus Q over T. Now, if, therefore, and there's no other delta S, because delta S within the engine itself is 0, because it's a cycle, it's a reversible cycle, therefore delta S within the engine is 0, and therefore the only thing which contributes to the total change in entropy would be this equation. And of course, we know that minus Q1 over T1 would be negative because of that negative sign. But this is actually contrary to the second law, because delta S being negative means that you are actually reducing the entropy in the universe. And we know that's not the case. This is not what happens. And therefore, that's against the second law. Therefore, we know that that cannot happen and is actually impossible to have. Let's just look at another example, which again is going to be impossible, but let's see why. Do you think we can have an engine which takes heat from the cold reservoir and rejects the heat to the hot reservoir? That is really the question here. You can see the direction of the engine, of the heat engine. Of course, the answer is no, but then you can explain that by this very simple equation. We've got two components, delta S1 and delta S2. Delta S2 in here is minus Q2 over T2. Again, minus sign because the cold reservoir is losing heat. Delta S1 is actually going to be positive because this time hot reservoir is actually receiving heat, and therefore it's positive. When you add them up together, assuming that, for example, Q1 is equal to Q2, then you can factorize it with respect to Q1, and then you get that fraction. And again, we know that that's going to be less than 0. And the reason why it's actually going to be less than 0 is because 1 over T2 is going to be bigger than 1 over T1. And that suggests that 1 over T1 minus 1 over T2 is going to be less than 0. And therefore you get that in here. Once again, you get negative delta S, and of course you get T2 minus T1, which is not possible because the cold reservoir can't be at a higher temperature than the hot reservoir, and therefore that cycle is going to be impossible. The only possible scenario is when you have this type of configuration, as we know. And the reason is shown here, again, by the fact that you've got two components of the delta S. Delta S1 being equal to minus Q1 over T1. And delta S2 being equal to Q2 over T2. Again, notice the sign. This is positive, this is negative. So you add them up, and this is going to be actually bigger or equal to 0. Now, and we know that, but what this implies is that Q2 over Q1 minus Q2 over Q1 is going to be less than minus T2 over T1. This is just by rearrangement of this balance. And I'm just going to put 1 minus this less than 1 minus this, adding 1 there. What is important here is that this implies that this, which is the thermal efficiency, will be less than the reversible efficiency. If you don't remember these, see page 7.10 and 11, where we talked about efficiencies for both a real cycle, and a reversible one. And really this proves that the Carnot engines are the most efficient engines or designs, because entropy is not produced. We're not going to spend a lot of time on Carnot cycles and Carnot engines, but this is just one of the references that we make, because this is really the basis of the Carnot engines, which you're going to be looking at that a lot in the future. Okay, so this one is what is acceptable and what satisfies the first and the second law of thermodynamics. Now, this is, I think, where things get interesting. And it sort of moves away from the theoretical stuff a little bit. So, remember the heat engines, the hot reservoir, the cold reservoir, we covered all those. What is really the engineering basis of the heat engine is actually what goes inside the engine itself. Even though in most of the theoretical stuff that we've done, we didn't do a lot with the actual engine and its design, but what we know is that this engine could have different forms. It could be in the form of a Carnot engine plant, it could be in the form of a refrigeration cycle, anything really. And the two reservoirs are just there to facilitate the function of the engine itself. So let's just look at the engine in more detail. I'm just going to use one example, which is the direct heat engine, and this one is, for example, so this is the direct heat engine that we introduced, and it's actually just opposite to what we introduced as reversed heat engine. Not reversible, reversed, which was the opposite. So if you think about a refrigeration cycle, that is a good example of a reverse heat engine. But this, what you see here, is, for example, what could be a power plant. And it is actually, in fact, a vapor cycle power plant. Regardless of what this power plant is based on, and I said this before as well, so if it's nuclear, if it's gas, if it's coal, whatever the heat of source, the source of heat really, and the heat source is, we don't care about that, because that heat source from the core of that generator or that power plant comes from there. What happens after that point is common in most of the power plants. So that heat could be coming from the uranium, or that could come from burning natural gas, or that could be coming from burning coal. That doesn't really matter. When the heat comes from that center or the core of that power plant, the rest would, you have all these four components in order to be able to produce this work, because this is the work that would generate energy and electricity. So let's look at these four components. But before that, let's just remind ourselves that the first law, when applied to a cycle, and of course this C represents cycle. By the way, I don't know if I mentioned, but you see this integral with C, which represents a cycle. This is the same as that. You might actually come across this integral with a sort of a circle in the middle in some textbooks, but they exactly mean the same thing. So for a cycle, as far as the first law is concerned, you have the integral of delta W equal to the integral of delta Q. And because we know that Q can be related to TdS, we can use that information as we will see in a moment. Let's look at the TS diagram for the cycle that you've got in here. By the way, let me just introduce the 4 components here. Starting with the boiler, that could be an evaporator, for example. Sometimes you see in some cycles. This is the turbine. A cooling, this is the condenser. That could be in the form of a cooling tower, for example. And this is the pump, or it could be compressor. And then this is the direction of the cycle. So that's the heat which you get from the hot reservoir, which could be the center, the core of the power plant. And this is the heat which you essentially reject to the cold reservoir, which could be a pond, a lake, a river, a sea, etc. Okay, so the TS diagram for this cycle, depending on at what pressure you're operating your power plant, there are 2 curves. One curve is here, which I show by red. This is the low pressure cycle. And the other one is this one, which is the high pressure cycle. Thinking about the low pressure one, which I think is more relevant to what we've been doing so far in terms of going through these phases, you can see we've got 2 key points in here and here. This is the saturated liquid point. This is the saturated vapor point. And what happens is that as the flow goes through the cycle, the low pressure cycle, first of all it becomes saturated. Then you get to this stage. The temperature is not going to rise because you're changing the phase of your liquid from liquid to vapor. So from water to vapor, that happens here. Therefore, you have latent heat. And then once you get to that point, when you've got dry saturated vapor, then you start heating up again and temperature goes up and it becomes superheated. Of course, when it's a high pressure one, you don't go through these phases and it just essentially goes to superheated and supercritical state. But that is beyond our course. You'll do this, I think you come back to this later on in the second or third year. So that is essentially a revision of what we've been doing so far. But the most important thing for now is that this line is essentially a constant temperature line, and these are constant pressure lines. So I now want to start looking at the individual performance of each of those 4 components within the engine itself. This is probably the simplified, or it's the simplest version of the TS diagram for a power plant. If you look for a more realistic TS diagram or PV diagram for power plants or other cycles, you see a lot more different type of combinations. But for now, let's just look at a very simple one. And so here, this is going to be the boiler, this line. This line here is going to be the condenser. Condenser. And of course, you can tell because boiler and a condenser, what they do, they just change the phase of your water in this example. And because they only change the phase, they're not changing the temperature of the water. And therefore, the temperature stays the same in both cases, because heat is there in those devices are just through latent heat, and it's just consumed in order to change the phase. In the other two devices, this one is the pump, which could be a compressor as well, and this is the turbine. And remember, I said earlier that pumps and turbines and compressors are all isentropic devices. So entropy across these devices isn't going to change. And this is what exactly we did in some of the examples that we did in the past, where you had a turbine. We said that S1 and S2 before and after are going to be equal to each other. And you see that here on this diagram as well. So there are two categories of processes, if you like. We've got the isothermal reversible processes, which applies to the boiler and the condenser. And you've got the adiabatic reversible processes, which are essentially isentropic processes, and that applies to the turbine and the pump. Now, if I want to start thinking about the heat now, so delta Q, for all these four lines, let's start looking at them one by one. Starting from the boiler, this is the boiler. I'm just going to zoom out so you can see both. The boiler, if you want to think about what is the Q, the amount of heat for the boiler, remember I related Q to TDS, and I said it's the area under the curve. Well, here you can plot and you can calculate the area under the curve as well. Now, as far as the Q for the boiler is concerned, it is actually TA, which is this point or this line, times SB minus SA. So effectively that would give you this area here, all this area under the curve. Okay? What about the second device, which was the turbine? Now the turbine, there was no change in S, and therefore Q is going to be equal, so the change of entropy is going to be equal to 0. And as a result, delta Q will be equal to 0 as well. So that is simple. The third one is the condenser. It's actually quite similar to the boiler. The way that you calculate Q for the boiler is TC. Let's just show you what that is. That is that line multiplied by SD minus SC. So that minus that, which then essentially gives you this line, this curve here, this area. And the last one is for the pump. And again, because this is an isentropic device, the change of entropy across it will be 0, and therefore QR will be 0 as well. So if you want to calculate the integral of the reversible Q for the whole cycle, it's going to be the combination of all the four Q's that we calculated. So this and this were 0, And the other thing that you notice is that, of course, SB minus SA, looking at here, SB minus SA will be equal to minus SD minus SC. As a result, the overall delta QR for the whole cycle works out to be TA minus TC, so TA minus TC, times SB minus SA. So effectively, this area would be the total amount of QR for the whole cycle. It is essentially the difference between what you had for the whole thing minus this bit. Going back now to the first law, and we said that QR, delta QR, is equal to delta W. It just essentially means that W, delta W now has to be equal to that as well. Now, what is the implication of that? There are three implications, as you can see in here. Let's just look at those one by one. A reversible cycle, the work done, remember the work done is the one that you're interested in, is the one that you get out of the heat engine, it's the one that comes out of the turbine, and it's the one that will generate electricity for you. That is the area enclosed in the T diagram by this area, A, B, C, D, A. So the area which I've shaded, that is the work done. The heat supplied to the reversible cycle is, in fact, as I mentioned earlier, is this bit. And the heat rejected from a reversible cycle is really this bit. So I hope you can now identify those three areas which represent the work done, the amount of heat supplied, and the amount of heat rejected. Why is it important? Well, when you think about the efficiency of a cycle, of course that is what you've been given, or the output, divided by what you've provided to the system. So you have provided the heat supplied to the cycle, and that heat was in the form of, as I said, coming from the nuclear reactor or a gas power plant. And the work done is what you get out of the turbine as a useful work that you can generate electricity with. That and that, as you can see, will be cancelled. And you're left with TA minus TC divided by TA, which is further simplified to 1 minus TC over TA. Now, this is, in fact, in agreement with what we defined as the absolute temperature. Absolute temperature, if you want to see that, if you don't remember, if you go to page 7.10, that is where we defined an absolute temperature. That was one of the corollaries of the second law. And the cycle which you've just seen in here is actually what we call the Carnot cycle. As I mentioned, you're going to be looking at Carnot cycles and some of its features in the second year in more detail. But for now, just be aware that this is really an ideal engine. So in reality, it can't happen, but it's the basis of a lot of the designs that are out there now. So you sometimes wonder why we make so many assumptions, and occasionally most of these assumptions actually are unreal. Well, if you want to design something that is real and is practical, you have to start with the principles, with the basic principles and the basic equations, and for that you need to make some assumptions. And that's what we've been doing so far. in order to be able to introduce to you what the Carnot cycle is, we had to go through those theoretical and all those assumptions to then be able to tell you then, well, look, this was the basis. Now these are the losses. These are the real conditions that happen in reality. And this is what the TS diagram looks like for a real power plant. Anyway, so let's look at this example. We've got an aircraft gas turbine which has these three components: a compressor, a combustion chamber, and a turbine. And well, you've got essentially the propelling nozzle as well, but that is not what is included in our calculation in this example, as you'll see later. We're just going to focus on compressor, combustion chamber, and the turbine. But typically, in a typical jet engine or gas turbine engine, these are the four components that you've got. So what is the question? Draw a schematic of the gas turbine. Then this is the bit which we are given all these conditions. This is the diagram. This is the conventional way of drawing a compressor. So if you've got a compressor, the air then goes through the combustion chamber or the burner, and then it comes through the turbine, and then it goes through the nozzle. But anyway, that is not what we take into account. Before I give you all those numbers, let me just introduce to you this diagram, because it's quicker a bit. It might be confusing, so it's worth explaining this. Subscript correspond to before and after. So whenever you have T1, P1, that means that is just before the compressor. And of course, T2, P2, that means after the compressor. Superscript, C, corresponds to the compressor. B corresponds to the burner or the combustion chamber. And T corresponds to the turbine. Now, for a problem like this, you have to go stage by stage. You have to start looking at each device one by one, and then try to apply your equations to each component. What we know, we know what is the temperature at the entrance of the compressor, 1 bar 278 Kelvin, which is a typical type of condition at sea level, if you like. And then, after the compressor, the pressure is 10 times more, as the question mentions here. So it's 10 times greater, as you can see here, the pressure at the outlet of the compressor. What then happens is that it goes through the burner. The temperature at the outlet of the burner is 1500 Kelvin, but the pressure hasn't changed. So a burner, in this case, is an isobaric device. So it's only the temperature actually has risen. Then what we have is that we've got that 1500 Kelvin would go through the turbine at the pressure of 10 bar, and we want to know what is going to be the T and the P at the outlet of the turbine. And at the end, you need to draw a diagram to show that behavior on the TS diagram. Some of the assumptions that we've got the value of R, CV, and gamma. Of course, we have these values because you're dealing with air, and air is, in this case, a perfect gas. In most cases, air would be considered as a perfect gas. And therefore, it suggests that at some point you will be using some of the things that we've been showing for ideal gases and perfect gases, some of those equations. The ones that I actually emphasize that these are very important to know and to be able to derive. So the starting point for this, we haven't got much time, so the starting point is the steady flow energy equation. We're not interested in the honest steady terms, so this is only steady. That equation, which you've also seen before, we used that in the previous example that I think we did last week when we were dealing with the turbine. If you don't remember where this comes from, this is from page 5.3. But essentially, just a reminder again, EH is essentially E plus PV, which is U plus half rho V squared plus GZ plus PV. That is the internal energy. So starting from the compressor, it is an isentropic device, and therefore that equation is really simplified to H2 minus H1 equals minus WS. S obviously is the shaft work for the compressor. And naturally there's not going to be any Q, so Q is equal to 0. That's why you end up with minus WS on the right hand side. This is the important bit, because with the ideal and perfect gases, you don't normally deal with entropy. It's not something that is easy to calculate. So what you need to do is you need to somehow relate it to other things. And those other things you can see here, because dH is equal to Cp dt, and this allows you to write that H2 minus H1 is equal to Cp T2 minus T1, which is equal to minus Ws. So this is a much better equation for us to use, and it gets rid of the enthalpy, and we don't have to deal with enthalpy as such. So, when it comes to a stage like this, you know what is the pressure, because you know that the compressor is compressing the air by a factor of 10. What you don't know is what is the outlet temperature after the compressor. So, this equation, which is key in here, would be relating your T and P for an isentropic process. You're wondering how on earth you got this power? Well, if you look at, remember there was a page that on Monday I said put a smiley face or whatever works for you. That is the page where you had those equations. If I can find that. Yeah, that is page 8.15. I'm now using this one. So that was T P1 minus gamma over gamma is constant. And by rearranging this equation, and again note that the power here is just slightly different to this because there's a minus sign here. I'm sure you can realize that when it comes to the rearrangement. But please don't be confused with this, because even I think on Monday I had some questions after the lecture asking about whether there's a mistake in the calculation, but in fact not noticing that the powers actually could be different. Anyway, you have this pressure ratio, you have the value of gamma, you can insert those values. You also know the temperature T1, and that allows you to find the temperature at the outlet of your compressor. The equation for the combustion chamber is actually quite simple, very similar to what we had for the compressor. The only difference is that now for turbine, for the combustion chamber, you don't have any work, there's no shaft, there's only heat. So H2 minus H1 is equal to Q. And we established that we can replace H2 minus H1 by CpT2 minus T1. So that is all we need to care about as far as the combustion chamber is concerned. Moving on to the turbine, it's exactly the same as a compressor. The only thing that you realize, we'll come back to this actually in a moment, because there's a difference in terms of the shaft work in the direction. And that difference is this. the shaft work, actually there's a typo here. This should be W shaft for the compressor. So all you notice here is that the shaft work for the turbine and compressor are just opposite to each other. And that is natural because of the direction of work. What that implies is that as far as the temperature difference is concerned, T2 minus T1 for the turbine is going to be opposite to T2 minus T1 for the compressor. There's going to be a minus sign here. This now allows you to find the temperature at the outlet of the turbine. And the last step is again to use the PT diagram, the TP equation, in order to find what P2 is. Please do some practice in terms of TP and PT equations that we've used so far. So looking at this one and this one here, I want you to be very comfortable with doing these equations, deriving them, playing around, moving them around, changing the power, the ratio, etc. Because if you can do those steps, it can save a lot of your time when it comes to any questions that you're going to be doing. And finally, it comes to the TS diagram. And in the TS diagram, as you can guess, you have an isentropic line for the compressor, an isentropic line for the turbine, and a typical isobaric line or an isobar for the combustion chamber, connecting the three devices together. Okay, so that's it. That's the end of our Chapter 8. So next week, the plan is for us to go through past paper 2017, and the week after we're going to go through past paper 2016. On Tuesday you've got your quiz, your assignment. So please make sure you read the instructions. Hopefully we're not going to have any problems this time. And yeah, good luck. I'll see you all on Monday.